Welcome to the deep dive. Today, we're really getting foundational. We're tackling the laws of motion and force. Basically, the rules for how anything, and I mean anything, moves in the universe.
Yeah, it's like the universe's instruction manual, isn't it?
Oh.
We're looking at sources that cover kinematics, how things move, and dynamics, why they move. And our goal today is, well, to cut through the jargon, we want you to get those aha moments about velocity, force, all that stuff.
Absolutely. And we should give a shout out here. Our source material, including some really clear explanations from Fizik, excerpts, HACI, VELİ, TORUN, has been fantastic for this. Really helps lay it out. The idea is you'll finish this and suddenly see physics happening everywhere, like when a car brakes or, you just toss a ball.
Exactly.
Correct.
Less about the equations on a page, more about understanding the concepts, velocity, acceleration, force. It's the language the universe speaks.
Okay, let's jump in. Describing movement. We use speed and velocity almost. Well, interchangeably, don't we? But physics says, nope, they're different. What's the actual distinction there?
It really boils down to one thing, direction. Speed is just a number, a magnitude. 80 kilometers per hour, that's speed. How fast you're covering ground.
Right, a scalar. But velocity, that needs direction too, like a vector.
Precisely. So 80 kilometers per hour north, that's velocity. Magnitude and direction.
Okay, but why fuss over the direction? Why is that so important?
Well, think about driving. Imagine you're going around a curve, holding your speed perfectly steady at, say, 80 kilometer. Your speedometer doesn't budge, right? Your speed is constant.
Yeah.
But because you're turning, your direction is changing every single moment. So your velocity is actually changing.
Yeah.
Constantly.
Ah, okay. So even if I'm not speeding up or slowing down, just turning the wheel means my velocity is changing, which leads straight to acceleration, doesn't it? Because acceleration isn't just hitting the gas.
Exactly. That's the key insight. Acceleration is any change in velocity over time. So speeding up, that's acceleration. Slowing down. Also acceleration, just in the opposite direction. We sometimes call it deceleration, but technically it's still acceleration. And turning, absolutely. Turning at a constant speed is still acceleration because your direction vector is changing. Think about your car again. Gas pedal, brake pedal, steering wheel, all three control acceleration. They change the velocity vector one way or another.
Okay, let me try and connect that. When you take a really sharp turn, you feel pushed outwards, right, into the door. Is that directly related to this acceleration, this change in direction?
Yes, precisely. What you're feeling there is often called the centripetal force, or the effect of it. Your body wants to keep going straight, that's inertia, but the car is forcing you to turn. That requires a force pointing towards the center of the curve. That force causes an acceleration towards the center. What you feel like is an outward push is really your inertia resisting that inward acceleration.
Yeah.
It's a direct consequence of changing your velocity vector's direction. The faster the turn and the tighter the curve, the greater the acceleration and the stronger that push you feel.
All right, so we can describe motion. Now, why does it change? That brings us to Newton, Newton's first law, the inertia one, right? Things stay put or keep moving steadily unless something pushes or pulls on them. A net force.
Spot on. It's all about inertia, an object's inherent resistance to changes in its state of motion.
And that resistance, that inertia, that's linked to mass, isn't it?
Directly. And this is where we hit that classic point of confusion, mass versus weight. They sound similar, we use them loosely. But in physics, absolutely critical difference. Why does it matter so much?
Well, mass is intrinsic, right? It's the amount of stuff in an object. It measures inertia. And crucially, your mass is the same whether you're here on Earth or floating out by Jupiter. It doesn't change.
Exactly. Mass is fundamental to the object. But weight is totally situational. Weight is the force of gravity pulling on that mass. The equation is W equals mg. Weight equals mass times the acceleration due to gravity, g.
And g changes depending on where you are. Like on the moon, gravity's weaker, so you weigh less. About a sixth, I think.
That's right. Same mass, much less weight. So mass resists acceleration, while weight is a force, the force that causes acceleration in free fall, for instance.
Okay, that clarity makes Newton's second law of ivme makes so much more sense. It connects everything. Force, mass, acceleration.
It's the heart of dynamics, really. F net equals ma. The net force on an object equals its mass times its acceleration. It tells you that acceleration is proportional to the force, double the net force. You double the acceleration.
Right.
And it's inversely proportional to mass, double the mass, but keep the force the same, and you only get half the acceleration.
Which explains why pushing a shopping cart is way easier than pushing a car. Same push, vastly different mass, vastly different acceleration. The car's inertia wins.
Exactly. Now, you mentioned Newton's first law: objects keep moving at constant velocity.
Yeah.
But, in the real world, things don't just keep rolling forever, they stop.
Yes, something always seems to slow them down.
And that something is usually friction. It's the spoiler for the first law in everyday life.
The unseen force.
Pretty much. It comes from, microscopic interactions between surfaces rubbing together. There's static friction, the force you have to overcome just to get something moving. And then there's kinetic friction, the force that resists motion while something is moving.
And friction depends on how hard the surfaces are pressed together, right?
Very much so. It depends on the normal force, that's the support force pushing perpendicularly between surfaces. Press harder, the normal force increases, and generally so does the friction. Without friction, things would behave much more like Newton's first law predicts. But here on Earth, friction's always there opposing motion.
Okay, moving on to gravity's effects. Before Newton really nailed gravity, Galileo did some clever work. What was his contribution again?
Galileo. Yeah, his work was ingenious. See, things fall pretty fast, and back then, measuring that speed accurately was, well, basically impossible. So he used inclined planes ramps, essentially. By rolling balls down gentle slopes, he diluted gravity, slowed the effect down enough so he could actually measure it. And what he found was crucial. The balls didn't just roll, they accelerated. And they did so uniformly. Their speed increased by the same amount each second. This laid the groundwork for understanding gravitational acceleration.
G.
Right, G. And when we talk about free fall, we mean something falling only under gravity's influence, with G being that acceleration. Near Earth, it's about 9.8 meters per second squared, often rounded to 10 for quick calculations.
Yeah, roughly 9.8 meters per sec. So drop something, ignore air resistance for a sec, and after 1 second, it's moving at 9.8 meters. After 2 seconds, 19.6 meters. 3 seconds, 29.4 meters, and so on. It keeps speeding up.
And the amazing part, the thing Galileo supposedly showed dropping things off Pisa, is that G doesn't care about the object's mass.
Exactly. In a vacuum, drop a feather and a hammer, they hit the ground at the same time, because gravity accelerates them equally, regardless of their mass. It's a mind bender, but true. And the distance covered, it's not linear. It goes up with the square of time. The formula is d equals 1/2 gt squared, so you cover way more ground in the third second of falling than you did in the first. Okay, but like friction, we don't live in a vacuum. There's air. Air resistance, how does that change free fall?
Right. Air resistance is basically friction with the air. And it's a force, R, that pushes up on a falling object, opposing gravity's downward pull, MAE. And crucially, air resistance usually gets stronger the faster you go.
So as you fall faster and faster, the upward air resistance force keeps increasing.
Exactly. It increases until, eventually, it becomes equal in magnitude to the downward force of gravity, the object's weight.
So the upward force R equals the downward force MAE.
Yep. At that point, the forces are balanced. The net force on the object becomes zero.
And if the net force is zero, Newton's second law says acceleration must be zero.
Bingo. The object stops accelerating. It doesn't stop falling, but it stops speeding up. It continues to fall at that maximum constant speed.
And that's terminal velocity.
That is terminal velocity. It's why skydivers eventually reach a steady speed before opening their parachute. And the parachute, it just dramatically increases the surface area, which cranks up the air resistance, R.
Making R equal mg at a much slower speed.
Precisely.
Yeah.
So you get a much slower, safer terminal velocity for landing.
Okay, we've described motion, explained its cause with ivme. Now for the third law, Newton's third. This is the action-reaction one, right? For every action, there's an equal and opposite reaction. Sounds simple, but I feel like this one trips people up.
Oh, it definitely does. It's the law of interactions. Forces always come in pairs. You can't have a push without something pushing back.
But here's the confusion I always hear. If I push on a wall, action, the wall pushes back on me equally hard, reaction. Why don't those forces just cancel out? Why does anything ever move?
That's the absolute crucial point. The action force and the reaction force always act on different objects. They never act on the same object.
Different objects. Okay.
So your push is on the wall. The wall's push is on you. To see if the wall moves, you look at the forces on the wall. To see if you move, you look at the forces on you. Since the forces are on different things, they can't possibly cancel each other out in terms of the motion of a single object.
Got it. The cancellation idea comes from thinking both forces are on the same thing, but they aren't. That helps. So let's apply that. Walking, how is that action-reaction?
Okay, when you walk, your foot pushes backward and maybe slightly downward on the earth. That's the action. The earth, in reaction, pushes forward and slightly upward on your foot.
And because my mass is tiny compared to the Earth's.
Exactly. That forward push from the Earth makes you accelerate forward noticeably. The backward push on the Earth, well, the Earth has enormous mass, enormous inertia, so its resulting backward acceleration is basically zero. You move, the Earth pretty much doesn't.
Okay, that makes sense. What about a rocket in space? People think it pushes off air, but it doesn't need air, right?
Correct. A rocket works perfectly in a vacuum. The rocket engine forcefully expels hot gas backward. That's the action. Rocket pushes on gas. The reaction is the gas pushing forward on the rocket. That forward push from the gas is the thrust that accelerates the rocket. It's a perfect third law pair, no air required.
And even gravity, is there an action-reaction pair there?
Absolutely.
Yeah.
The Earth pulls you down with a force we call your weight. That's the action. Earth pulls on you. The reaction. You pull the Earth up with an identical, oppositely directed force.
Seriously, I pull the Earth up.
With a force exactly equal to your weight. But again, think ESMA. The force is the same, but the Earth's mass, m, is astronomical. So its acceleration, a, towards you is infinitesimally small, undetectable. You accelerate noticeably towards the Earth basically stays put. Same force, vastly different effects due to mass. Hashtag tag tag outro.
Wow. Okay, so wrapping this up, we've seen that motion is described with vectors, like velocity and acceleration. We know changes in motion are caused by net forces, summed up beautifully by ivme. And finally, forces never happen alone. They're always interaction pairs, equal and opposite, acting on different bodies. Newton's third law.
Exactly. And once you kind of internalize these ideas, you start seeing them everywhere. Driving, sports, even just jumping. You can analyze the forces and motion involved. It changes how you see the physical world.
Definitely gives you a new lens. So let's leave our listeners with a final thought, connecting gravity and that third law. We just said the Earth pulls on you and you pull back equally. But think about the moon. It's way less massive than Earth and super far away, yet its gravity has this huge visible effect, the ocean tides. Why is the moon's pull on the whole Earth so significant, causing tides, while, say, a heavy 10-kilogram weight right next to you exerts an equal gravitational pullback on the Earth that we can't detect at all? They're both third law pairs, right?
Ah, good one. It hints at something deeper than just the basic force equation. Think about the difference in the moon's gravitational pull on the near side of the Earth versus the far side. Because the Earth is so large, the moon pulls slightly stronger on the water closer to it and slightly weaker on the water farther away. That difference in force across the Earth is what stretches it and creates the tidal bulges. It's about gravitational gradients over large distances, not just the simple force between 2 points.
Differential gravity, okay? Something to chew on there. Fascinating stuff. And again, a big thanks for the clarity in our source materials today, including the work from Physik Öğretmeni HACI VELİ TORUN. Really helped structure this deep dive.